Good afternoon guys, and welcome to another worked exam answer video. This question is focusing on the ideas around organic synthesis from A-level chemistry. There are lots of reactions, as you can already see in this question, so you might be able to pick out specific reactions that you want to find out more about from this question, but I've chosen this question as a way of showcasing how they might address multiple different types of reactions all in the same question. And the organic synthesis topic, which appears in the sort of year 13 side of the course, there's no additional content in there. It's about kind of it's a hint that you're going to need to know the connections between different homologous series, and to give you a chance to practice looking at reaction schemes like this and identifying what all the different processes are within that reaction scheme, or perhaps putting together your own synthetic route. And if you are to do that, it will have a maximum of 3 steps, whereby you might be asked to go from a halogenoalkane through to, my brain's gone a bit blank, I'm trying to think of 3 steps, but we could go from a halogenoalkane to a carboxylic acid, for example, via an alcohol. So we do need to essentially, for any organic synthesis question, whether it's one like this or whether it's one where you've got sort of gaps that you have to fill into a reaction scheme, you've essentially just got to know all the organic reactions, inside out. Now, the best way, in my opinion, to do that is to have a big piece of paper where you've got all of the different homologous series spaced out on the page, and to draw arrows that show all the connections between the different homologous series, and then you can add on their names of mechanisms, names of reactions, conditions, etc. And then using that regularly will help you to rote learn that information and commit it to memory. But also then you could kind of play a little game of, I want to say matching pairs, it's not exactly matching pairs, but you'd write all the homologous series down on a piece of paper, cut it up into little squares, turn all the squares face down, and then you could choose 2 at random. And let's say we chose halogenoalkane and carboxylic acid, you would then be tasked with thinking, okay, can I go from a halogenoalkane to a carboxylic acid? And if so, how many steps do we need? I could make it a 3-step synthesis if I went via an alkene, because we can go halogenoalkane to alkene, then to alcohol, then to a carboxylic acid. And knowing all of those different routes it is just going to be so important, because it's going to mean that you can recognise what you need to do quickly. And if you're sat there going, oh my God, how do these things link together? That's going to end up being very time inefficient, unfortunately. So practicing things like that, and then once you've done your halogenoalkane to your carboxylic acid example, put the cards down, muddle them all up, pick another 2. And it might be that you can't go from one to the other because there's no set route, and that's also good to know. So yeah, that's how I would proactively go about revising for organic synthesis. Now, in this particular question, we've got 5 steps. Now, before we even think about what the question is asking us, I'm just going to go through and identify what all of these different things are, so that we can kind of see how important it is to be able to recognise different functional groups within compounds, and then obviously to know the different reactions as well. Okay, so the first structure, they haven't drawn any of it in displayed formula, but what we can hopefully see in there is that we've got a CO with a carbon either side. So that there is going to be a ketone. And then in step 1, we then turn that into an alcohol with a CN on there as well. The C double bond O is gone. We've now got a C single bond O. And then we've got the CN, which is making up the 4th bond for that middle carbon. So that is a hydroxy nitrile. And again, as soon as I see a ketone and then I see that the C double bond O is gone, we've got an alcohol, and regardless of whether we then had a H or a CN, immediately, and I know that I've got a lot more experience of this than you guys, but immediately I would be thinking that's nucleophilic addition. So step 1 is nucleophilic addition, and we're going to need to get the CN added on there. We're going to need to add something along the lines of KCN, and then we're going to need some sort of acid so that once we've broken up the C double bond O, the O minus lone pair can attack a H plus to make our alcohol group. So we're going to need HCN and something along the line, KCN and something along the lines of HCl. So that's step 1. Then what we can see has changed in step 2, or the product of step 2, we've now got a double bond in there. So at this point, the CN is not so important because the bit that we've changed is we've removed the OH group and a hydrogen from the CH3 to get our double bond in here. So this is then an alkene. And again, we need to be able to quickly recognise if I'm going from an alcohol to an alkene, that will be elimination. As a type of reaction, it's dehydration. And when we're doing elimination of an alcohol to get an alkene, we need sulfuric acid as our catalyst. In terms of step 3, going from a CN to a carboxylic acid in one step is not something that we need to know how to do. So again, it's really important that we know all the ones we need to know so that we don't then go about trying to learn ones that are not relevant. So we don't need to know anything about step 3, but we do need to be able to recognise that we now have there, in place of where the CN was, we have a Cu group. So we've still got the C double bond, but that hasn't changed from the product of step 2 to the product of step 3, and it doesn't change in the product of step 4. So the key thing here that we're looking at to see how it changes is the Cu group, which makes a carboxylic acid. Then we go from a carboxylic acid to a COOCH3. So again, we need to be able to identify that as a functional group, and having a COO that then doesn't have a hydrogen after it, but then has a carbon after it, we've turned that into an ester. Again, the C double bond C is still there, so that's not gotten involved at all in the formation of our ester. So we have done esterification. There is no mechanism that we would have to draw for esterification when we start with a carboxylic acid. So there's no mechanism, but we would need to be aware of what we would be adding, which is going to be an alcohol, specifically methanol. So CH3OH, and then in esterification, again, we use concentrated sulfuric acid as our catalyst. So those are things that we can put there. And then finally, we need to have a look at what's going on in step 5. Step 5, we've still got our ester. So what we've done now is we've removed the double bond between the carbons, and we've put the hydrogen back onto that CH2 to make it a CH3, and then we've put a hydrogen onto that carbon there. So we've gone from an alkene then to an alkane, and that's the bit that's changed if we're going from there to there. So then we've got to think about how can I go from an alkene to an alkane, and this is perhaps not one that you will be hugely familiar with. It links slightly into opening up the C triple bond N of the nitrile group, so that we can make CH2NH2, but also we need to know that when we do addition reactions with alkenes, that we can do those with hydrogen as well as things like a halogen or hydrogen halide or sulfuric acid. So step 5 would be achieved via electrophilic addition. We can also call it hydrogenation because we've opened up the double bond, added hydrogen to turn it into an alkane. So we're going to need some hydrogen gas, and then we're going to need to do that in the presence of a nickel catalyst when we're opening up either the double bond of an alkene or the CN triple bond to turn it into CH2NH2. Hydrogen gas, nickel catalyst will be what we've used. Now there is a heck of a lot going on in just looking at what we've done there in that reaction scheme alone. Now, identifying functional groups is key. Knowing reactions, conditions, names of mechanisms, also being able to outline the mechanisms in certain questions, all really important. So you need a proactive way of learning all of that content. And if you're stuck for some ideas, do not hesitate to ask. And then actually what this question has asked us to do, which because of how we've gone about looking at this question, we've essentially already answered, we've got to say which step is shown with a correct reagent and a correct condition. So in step 1, do we use HCN dissolved in water? Absolutely not. We've got to have KCN because HCN is toxic. So we don't use that anymore. Older questions will use HCN, but we don't anymore. It's got to be either sodium cyanide or potassium cyanide. And we're going to dissolve it in an acid so that we've then got our H+ to form our alcohol group. So it's not step 1. Step 2, KOH dissolved in warm water. Not sure what they're hinting at there. That's just completely wrong. I don't know whether they're thinking about, well, if we had KOH in warm water, we'd be doing nucleophilic substitution, and we're not. We're doing elimination of an alcohol to an alkene, so that is just absolutely completely wrong. Step 4, we've got methanol. Yes, we definitely do need to add methanol in step 4 so that we get this ester here with an alkaline catalyst. Nope, it needs to be an acidic catalyst. So it's not going to be answer C, and therefore again by process of elimination we've worked out that it is going to be answer B, but based on what we've already written down we can confirm that in step 5 we need hydrogen and a nickel catalyst. Yes, we do. Now of course you're not going to be doing all of that in a multiple choice question, but there will be other questions within the main body of the paper where you might get something like that, and then they could ask you about any of those steps. They could get you to draw mechanisms, name mechanisms, give reagents, give conditions, anything essentially organic skills based. And that's why synthesis is hard. It's not because each individual reaction is necessarily hard, because you've covered all of those already. It's how it all comes together. It's that big picture thinking, and that's why having all of the different homologous series and how they connect on one big piece of paper, for me, feels pretty fundamental for organic synthesis. Okay? Any questions about any of that, of course, please do not hesitate to get in touch. Hopefully that's been useful, and thank you so much for watching.